Hello, good morning, everyone. I want to welcome you to another statistical learning class. Of course, today the focus is going to be on Bootstrap. Before now, we started what I call module, assessing module accuracy. Of course, the way to tell if a module is doing a great job is to have a way to evaluate the model performance. And I remember before now, I walk you through several ways of assessing that, which I call cross-validation. Of course, in the cross-validation, I walk you through validating test approach. I walk you through leave out, and I walk you through um, the one that has to do with K-fold validation. Now, let me tell you this, all that way of assessing model work if the we know the functional form of the model, and not only that, um, the variance formula is not complicated. So, but what if in a situation where the asymptotic property fails? Asymptotic property actually work in situation where we're dealing with a large sample size. So what if in a situation where we're dealing with a large or with a small sample size, or we don't even know the functional form of the model? Because if I don't know the functional form of the model, there's no way we're actually going to simulate data from such model. Or even if we know the functional form of a model, the variance is complicated. Like the variance of estimator, using a model is complicated, and we want to assess our model. So the alternative option to cross-validation is Bootstrap. Okay, I want to welcome you to Bootstrap. Okay, in the outline, of course, I'm only going to say I'm going to walk you through two types of Bootstrap. Okay, we have a non-parametric Bootstrap, and we got parametric Bootstrap. But let me tell you this. The whole thing will start, if I want to conduct analysis, the whole thing is actually going to start from trying to get to know our data set as explained by John Tukey in 1970. Okay, on his article on data exploratory analysis. So we need to do a detective work trying to figure out the descriptive analysis, conduct descriptive analysis where you're trying to get to know your data set. And one of the preliminary steps in data exploration is generating plots like the one I'm showing now, density plot. It could be histogram. You can sketch histogram. You can sketch stem and leaf. You can sketch a box plot. But right now, I'm actually displaying density plot. Okay. The idea is just, okay, what is the distribution? What is the probability distribution of my data set? If you look at what I'm displaying now, for instance, maybe I'm interested in determining kurtosis. In statistical analysis, we got what we call skewness and kurtosis. Skewness measure departure of the departure of the distribution of data from normality, but why kurtosis handle measure what I call the pickedness. of a distribution. So it measures the peakiness. Okay, peakiness. Okay, with cortices, you'll be able to know whether the tail in the distribution is fat or not, and the peak as well. You want to know the sharpness of the peak. Okay, now how am I going to identify if the distribution of data set is normal by skewness? Of course, skewness is going to be zero. When skewness equal to zero, of course, I know the distribution is symmetric. When kurtosis, okay, by measure, when kurtosis, okay, equal to 3, or when the SS kurtosis equal to 0, it's another way to know that we're dealing with the symmetric data. Now, we have three different type of cortices. We have mesocortic. Mesocortic is for normal distribution. Mesocortic. Okay, when the cortices is mesocortic, okay, that is normal. It means the data set is normal. If it is leptocortic, most of financial data are leptocortic. They have fatter tail. Okay, so the cortices is going to be greater than that. And when it is a flaticortic, it's going to be that. So when you see the shape, you know what I'm displaying now. You see the green one is a platycortic. You see the black one is the one for normal distribution. And if you see the other one, the leptocortic, when you see that, then you know, yeah, it is not normally distributed. Let me now say this. Maybe I'm trying to work on financial data like stock returns, okay? And I want to have a sense of the probability distribution of returns, okay? One of the measure that I need, one of the basic statistical measure that I need is kurtosis. And I want to estimate kurtosis, okay? I want to estimate kurtosis. Okay, if I want to estimate kurtosis, I'm going to be using estimator, right? But you know what? Estimated kurtosis, I realize if I want to assess the estimate, the reliability of the estimate from the formula, okay, then I need to have a way to measure uncertainty in that, which means I'm going to be targeting variance. But in this case, the variance of when the variance of an estimator is complicated and I want to assess the performance of the model, then I need a bootstrap. I'm going to say that again. The interest here, I want to estimate kurtosis. I want to find kurtosis. And in statistical analysis, okay, when you particularly in statistical theory, okay, equation 11, okay, is a parameter. Okay, if I know y, if I know the mean of y, mean of y, the mean of y that you are seeing, okay, because I have a random variable y, which may be a stock return, okay, and the mean of y is the expected value of y. I'm only going to know the expected value of y if I know the density function of y. Okay, so this guy is a mu y. Then the variance of y, okay, is sigma square y. Okay, it's from the traditional statistic class that you're going to have expected value of y squared minus expected value of y or squared. You're only going to get access to this if you know the probability density function. What of in a situation where it is unknown? Does that make sense? If it is unknown, or it is known, but the variance of estimator is complicated. Now, if I want to estimate from sample, equation 11 is parameter theta. Okay, getting that exactly. If I know the expected, if I know the mu y, the sigma y from the distribution, all what I'm going to do is just to find the expectation of that guy. Okay, but you know what? Equation 12, because if I now have sample of data, I can use equation 12 to estimate. Equation 12, the theta cap that you see in equation 12 is an estimator. I differentiated the other time between parameter and estimator and estimate. Parameter is the population characteristic value that we're seeking to figure out. And the only way to get parameter exactly in this case, we need to know the probability distribution of y that will enable us to find the expected value of y, which is the mean of y, and the variance and the standard deviation of y. But if it is if that functional form is not in existence, okay, then I actually want to compute, I want to assess the performance of my model. And equation 12 is a model, it's an estimator that I actually want to use. I want to use that estimator, okay, because I've taken sample. Okay, now in the estimator now, I need to know the sample mean, this is y bar, okay? In the formula, I also need to know sigma cap y with the standard deviation. I need to know all of that from the data set. Okay, so equation 12 is an estimator. If I use equation 12 on different subset of data, equation 12 will give me different values. Does that make sense? Equation 12 is an estimator, and because if I actually train equation 12 on different subset of data, I'm actually going to have different values that make equation 12 a random variable. Then I want to know the performance of my random variable. If I want to know the performance of my random variable, then because I want to measure the uncertainty, because it's going to give me different values, then there's a room for uncertainty. How do I measure the performance of that? To measure the performance of that, I need the variance of the equation 12. I need the variance of a theta curve. Okay, the variance of a theta curve if I want to measure the performance of equation 12. Now, the variance of a theta curve, putting into consideration equation 12, the variance of it is not in a closed form. It's complicated. Complicated. And that is the reason why we need a bootstrap here. Okay? The one we did before, the variance of those estimator that we did before, they were not complicated. And that was the reason why we were able to use a cross validation. Does that make sense? So Bootstrap is an alternative way of assessing our model, the performance of our model in a situation where the functional form it does not exist, or even if the functional form exists, the variance of the estimator is cumbersome, it's complicated. Okay, I've already explained that. Different, we have an estimator, we have an estimate, we have a parameter. Okay, estimator is the method that you want to use. Right now, we want to figure out kurtosis. We're going to use a formula. We're going to use a method. The formula we're using, the method we're using is called estimator. And what we want to know is the performance of the formula we're using, the performance of the estimator. Why do I want to know? Because the estimator, when I train that on different data set, is going to give me different results. Okay, that's exactly what I'm trying to say here. I said in general, if we want to attach a measure of uncertainty to our estimate, then we need to know the distribution of the estimator. Let me tell you this. If something gives you a result that varies, if something give you results that varies from data set to the other, then that very module that give you something result that vary is a random variable. Then if it is a random variable, then we need to know the probability distribution of a random variable. And that's why they say here, we need to know the distribution, or at least we need to know how the variance look like, because it gives result that vary. Variance exists for it. That is the meaning. It gives result that vary. There's variation. Okay? So that's what I mean. Unfortunately, this is not easy to do mostly when we don't know the distribution of y. That was what I was saying here the other time. We don't know the probability density function of y. And that will be difficult to tell. But the good news is the Bootstrap can handle that. Okay, now I'm going to place, I need you to pay attention. I need you to pay attention. What I want to demonstrate now, I want to first focus on non-parametric bootstrap. Non-parametric bootstrap. We got two types of bootstrap that I want to discuss in this class. The non-parametric bootstrap is the one that doesn't rely on assumptions, like we don't even know the functional form. Okay, so now this is what we're going to do with a non-parametric bootstrap. We have set of data. The set of data that you have is this. Please pay attention. If you don't understand this question, take a look at this. That is a set of data that I have. Originally, how many of them? 5. This is too small. Using the approach of cross-validation that you've done, it can be trusted with small sample. Because with this, asymptotic property will fail. You know what we call asymptotic? Large. Okay? As something goes to infinity, large, sufficiently large. This is not sufficient enough. Okay? What do I want to find? What am I looking for? I'm looking for kurtosis. The very first thing I'm going to do in the first step, I will use the formula here to find the kurtosis. Formula in equation 12. Formula in equation 12, y bar, the mean of the data, the standard deviation of the data, plug that in, sum it, subtract the mean from the respective data. At the end of the day, you raise it to power 4, you sum it, you divide by n. That will give you that. So when you do that, that's going to give you initial value of a 0.83. Okay? Now after that, you now decide on the bootstrap. What do we mean by bootstrapping? Oh my God, bootstrapping. You have small set of data. You now want to make it big, like you want to bootstrap from that. Now, I have n equal to 5. Okay, I will decide on the number of bootstrap that I actually want to have. We normally prefer large values of bootstrap, like 10,000s. Okay, but here I'm only going to be showing 3. Does that make sense? Now, because of that, my b equal to 3. My b equal to 3 means I'm only going to have 3 bootstrap. Now, let me tell you the way the first bootstrap, I need to create a bootstrap sample, which means I'm actually going to sample from the original data set. My sampling will be with replacements. There are two types of sampling in statistical analysis. We have sampling without replacement and sampling with replacement. And and we're generating that randomly. So I need you to focus on this. This is the original sample. This is the original sample of data. This is the first sample bootstrap. what do you see? 1, 57, 57, 57, 3. Why is 57 repeated? Because I'm sampling with replacement. There's possibility of having a number repeated. Based on that, based on the first bootstrap sample, I'm going to use that formula again. The formula for kurtosis. You know, here the intention is to find kurtosis. I'm going to use that again, and I'm actually going to call that theta cap 1. That is the estimate for the estimate from first bootstrap sample. And that estimate give me 0.749. You see that? Now, I'm going to generate. We have a code to generate different kind of bootstrap. Now, another one, the second one, okay, I want you to pay attention to the second bootstrap is this guy here. Use the same formula again. You're actually going to have that until you get to the third one. Okay, to get a third one, in this case, how many values do I have? Because my numbers of bootstrap is 3, I'm actually having that. Can you see that? What am I going to do now? Then I'm going to find the average. Okay, finding the average, adding that guy up, divide by 3. Which means if you do it 10,000 times, you're going to divide by 10,000 by the numbers of bootstrap. And that will automatically give this guy here. Can you see that? Now, do you know with a bootstrap estimate, okay, with a bootstrap estimate, you can calculate some performance metrics. You can find bias, you can find variance, you can construct a confidence interval, and so on like that. Now take a look at this. Now, what am I doing here? Oh my God. What am I doing here? I actually want to figure out the variance of the estimator. What is the estimator? The estimator, don't forget, is a kurtosis, the formula for kurtosis. So what am I doing? What I'm actually doing now, okay, I'm actually subtracting this value from the mean, okay, square that value from the mean, square that value from the mean, square that, and I'm actually going to divide by 2. Why am I divided by 2? Oh my God, look at the formula. It's 1 over b minus 1 for variance. Does that make sense? B minus 1. Okay, but for the mean, you're going to add them up and divide by the number. For variance, you actually have that. Any question on this? Any question on this? Okay, now the issue that I have with this, using uh, repeated data in the sample. That is the issue that I have with that. Okay, now I want to go into parametric version of bootstrapping now. Parametric version. When I say parametric version, I just want you to see the difference between the non-parametric and the parametric. For the non-parametric, there's no any distribution specified for the non-parametric. No distribution specified. But for the parametric, okay, we know the distribution, but maybe the variance of the estimator may look complicated. And that is the reason why we want to use idea of a bootstrap. Now, this is the way it's going to work. We know the distribution, okay? And when we know the distribution, but we want to investigate the estimator. Let me tell you this, in statistical analysis, when I talk about estimator, when I have a distribution, every distribution is parameterized. I'm going to say that again. Every probability distribution is parameterized. What do I mean by is parameterized? Every distribution has parameter. Poisson distribution has a parameter lambda. Binomial distribution has a parameter NP. Normal distribution has a parameter mu and sigma, and so on like that. Every distribution has parameter. And what is the intention? What is our intention when we have a distribution? Oh, we want to estimate the parameter in a distribution. And estimating parameter in a distribution, we got some method of estimation. Like, has anybody heard about method of moment? Okay. What about method of maximum likelihood? Do you know I may want to investigate? If I want to estimate parameter from a given distribution, I may want to compare which method is going to work. Okay, is it going to be moment estimate or maximum likelihood estimate? If I want to know that, I will compare the variance of the estimator of the two. Okay, and that is what we call in statistical analysis, we call that we want to have a measure of relative efficiency. Okay, we want to see how well I have two estimator, which one is more efficient. Okay, I want to walk you through the way parametric bootstrapping work. Suppose we know the distribution, and the distribution is Poisson. Has anybody heard about Poisson distribution? Okay, Poisson distribution is a very good distribution for mostly rare event. Okay, now Poisson distribution has a parameter lambda, but you know what? That lambda is unknown. Parameter is unknown. So if the parameter is unknown, then it needs to be estimated. If I'm going to estimate parameter, I need an estimator. Does that make sense? But in this case, the estimator is actually the maximum likelihood estimator. Okay, the maximum likelihood estimator. Okay, let me quickly do this. If you have a Poisson distribution from what you've done before, okay, from what you've done before, if f of s equal lambda, okay, lambda raised to power x, okay. I think I'm not, man, don't let me do because of my time. But some of you, you've done what we call um, statistical theory, where um, you have a distribution and you want to estimate the distribution, the parameter, in the distribution using the method of maximum likelihood. This is a probability mass function for Poisson. Exponential is power lambda, lambda is power x over x factorial. Okay, if I want to use the method of maximum likelihood, okay, I'm actually going to find the product of both sides. Now, if I want to find the product, okay, the joint, we call that the joint, okay, the joint I'm actually going to have, there's going to be lambda raised to power summation s. Okay, this is wasting my time. I'll quickly do that on the board. That's wasting my time. Okay, I need you to pay attention. Okay, okay, um, I have s follow poi with parameter lambda, okay, f of s equal exponential raised power lambda, lambda raised power x over x factorial, s start from 0, 1, 2 to infinity. Okay, now I want to find, this is f of s. Okay, I want to find the joint. Okay, I want to find the joint. Okay, the joint is actually going to be this. I'm going to have that raised to power that n, lambda raised to power summation x, and this is going to be that. Okay, I start from 1 to n. Then after having the joint, then I'm going to take the log, okay, ln the product, okay, f of xi, okay, so ln of that, I'm actually going to have ln of that, if I'm going to have this one, okay, so which is going to be ln this, okay, plus ln lambda summation s minus ln that. Okay. Now, if I have this, so this is going to be, uh, so if I have that, going to be minus lambda n plus summation ln lambda minus ln that. Okay. Now, let me call this one my likelihood. Okay. And I want to differentiate that. Okay. Now, differentiating that with respect to the lambda, because this is method of maximum likelihood, with respect to lambda minus n respect to lambda plus summation over lambda. Okay, then I'm going to equate that to 0. Equating that to 0, I'm actually going to have this equal to n. Okay, my lambda cap mle now is going to be summation x, okay, over n. Okay, summation x over n, which is the mean. Okay, if you take a look at this now, the maximum likelihood, the estimator now, if I want to figure out the lambda, you know what it's telling me? Find the mean of the observation. Does that make sense? Now, in this case now, in what I'm showing you now, okay, we want to estimate lambda using the method of maximum likelihood, what I just showed right now. Now, which is the values of the mean. That was why I said it. Take a look at this, which means the original set of observation given, find the average. After finding the, now I don't just find the average, I derive to be able to know the, which means whatever distribution you're given, you need to be able to know the maximum likelihood estimator of the distribution. Okay, now the very first thing I'm going to do is whatever I got from the mean, I will now put it back into the distribution to simulate data set. Okay, if I want to simulate data set using Poisson, arrow poi, then I will indicate what I got. Okay, if I want to simulate like maybe five, then I will indicate the mean. Okay, so that is how parametric bootstrap work. We're going to simulate from a distribution, but you know what we're going to do? We need to specify, we need to get the maximum likelihood. Then after simulating, so we're going to have different, so many bootstrap. Okay, but here the difference is, compared to the non-parametric bootstrap, in non-parametric bootstrap, we are actually resampling from the original data set, but in the parametric bootstrap, we are simulating from the distribution. Do you see the difference now? Okay, now when you do that, when you draw the first bootstrap, you find the mean again. Second bootstrap, find the mean, and so or up to the whatever number of bootstrap that you have. You're actually going to have several values, I mean, several estimates. Then you can go ahead, find the mean of that, find the variance, just like what we did before. Now, there's an example here. Look at an example here. Please pay attention. I need you to pay attention. Okay? Now, you were given data set to be 150, 23, 57, and 3. The sample size is 5. And they told you this data set is believed to come from a Poisson distribution. Now, the very first thing you do, okay, because the maximum likelihood, okay, which is the estimate, maximum likelihood estimator for Poisson that we derive is equal to the mean. Then we find the mean of this original data set. Do you see what you have? 26.8. That is the mean of the original data set. It is this value of the mean that you're going to use as a parameter in a Poisson distribution to simulate data set. Does that make sense? Now, the belief is this is the first set of data you simulate. And after the simulating that, find the average. This is the average. This is the second set of data. This is the average. This is the third set of data. This is the average. But let me tell you this, you are not able to have the first set of data, the second set of data, the third set of data without you knowing the maximum likelihood estimate. That was what you plug in into the distribution for you to be able to generate sample from the distribution. And after that, here I'm only talking about three booster sampling. I'm going to find the mean. You see the mean? I'm going to add that up, divide by 3. Then I'm going to find the variance. That's how it works. It's super easy. Super cool, easy. Okay? Now, there's something I wanted to take note in the parametric, bootstrap. There are some values here that are not in the original sample. Did you take note of that? But in the case of non-parametric bootstrap, okay, you are never going to have an outside because you are bootstrapping from your sample. You did not go to larger population to take more sample. No, you are only bootstrapping within the sample you have. I provided some R code. I've updated the material. I just posted the updated today. You can check. Take a look at this. I've added this. This is how do we do undo parametric bootstrapping in R. I have observations given, okay? And when I find the maximum likelihood of the exponential distribution, it is the lambda is 1 over mean. The lambda is 1 over mean, okay? So which means to be able to simulate from exponential distribution, okay, I will need to supply the parameter, the parameter now, the estimated parameter based on the maximum likelihood, okay, of the parameter for that distribution. Does that make sense? Oh my God. How do we do it in now? That's what I'm doing now. You see now? Now, here now, this is the density function, okay, of the exponential distribution I'm using. Okay, f of s, okay, it is uh f of s equal lambda exponential raised power lambda s. This is exponential. The maximum likelihood estimator for lambda here is likely going to be 1 over x bar when you derive that. Okay, that's what we put. Okay, this is the first set of bootstrap. Okay, you see that? You see that? And that will continue to go like that. You do it again, do it again, do it again, continue to do it the way. But you know what? If you want to have a code where you specify the bootstrap sample, like we normally want like 10,000, 5,000, 10,000. Take a look at what I'm doing here. Do you see that? The number of bootstrap, 5,000. Okay, I supply that and look at the code. At the end of the day, look at what I got. Okay, Arrow will automatically give you what you want. The standard deviation of that, the variance of that, the mean of that, and so on like that. And Arrow is also automatically, you can also draw the histogram. Okay, the histogram of your estimator. Okay, not only that, you can you can construct the confidence interval for that. Did you know you can try this one? You can try that. What is missing? What do you want to estimate? This is a binomial distribution, right? Can somebody tell me? What does theta represent here? Extra credit. What does theta represent for binomial distribution? I have n comma theta. Theta represent what? Binomial. What does it represent? Do you know what it represents? Go ahead. The probability of something, right? You are very correct. Binomial distribution in statistics, if X followed by norm with parameter n theta, this is P. In statistic literature, you're actually going to see n combination S, P raised to power S, 1 minus P raised to power n minus S start from 0, 1, 2 to n. We use binomial distribution to module, variable with two possible outcomes: success, failure. P. So n is the numbers of trials. S is the number of characteristics of interest that we call the number of success. P is the probability of success. Like, what is the probability that a patient will be diagnosed with a disease? It's either the patient is diagnosed with a disease or not. So the theta now is P, the probability of success, the probability of the characteristics of interest. So right now, you have data set. Okay, you have data set. The intention is to, we don't know, even though we know the functional form is binomial, but we don't know the parameter is unknown. The very first thing you do is to estimate the parameter. Okay, you can use the method of maximum likelihood. Okay, after estimating that, then put that parameter into binomial distribution, then generate your bootstrap. Okay, and follow what we did before. Now I'll quickly give you this example. Please pay attention. Okay, I'm working on correlation analysis between uh SAT and GPA. Okay, now I have data set for LSAT, I have data set for GPA. What is my intention here? Correlation. Okay, now in R, the correlation, you can see that core between that, that gave me this, right? That gave me that. And of course, this is scatter plot, GPA and that. Okay, now the next thing I want to do now is, okay, uh, you know, I want to use a parametric bootstrap. Why am I assuming? Because the idea is that correlation should follow normal distribution. When we're dealing with correlation, the variable that are correlating, we expect a normal distribution. Now, because of that, take a look at what we take a look at this. Okay, normal distribution. Okay, and what are the parameters in normal distribution? The mean and variance, right? And I got two variables here. I need to find the mean of LSAT, the mean of GPA. Now I also need their variance covariance. Does that make sense? Two variables. I need the variances and the covariances. Okay, you know what I want to do now? Okay, because because why am I doing what I'm doing? Because I believe that this data set is not large enough for me to conclude that this is a correlation. It's not large enough. And I want to bootstrap. Okay. Now, in my boost, please pay attention. Take a look at the code. Okay. I'm going to load a package called mass. The number of simulation 5,000. Okay. Look at all of that. Okay. Now, when you put on the code, okay, this is the histogram. It's trying to tell you that is kind of skewed. Okay. You see what came out of that, and this is the confidence interval of that. Okay, so now this is trying to use a parametric approach, bootstrapping that data set for correlation. The estimator here is a correlation formula. Now if you want to go non-parametric way, okay, this is the non-parametric way. This is the code. You can try and run the code. And at the end of the day, you see you have the same. You have, it's also showing some kind of skewness. So I would advise that you look into all this. But what is the takeaway today? Okay, the takeaway from what we've done today is We're trying to look for other way to assess the model adequacy, and we realize there are times, the functional form of a model may not exist. And when it exists, okay, the variance of the estimator may be complicated. Okay? And another thing is the data set that I have, maybe the sample size may be small. Okay? And that is the reason why we consider bootstrapping our data set. Okay? And we got two ways to bootstrap. The first one is if we don't know the functional form at all, okay, all what we're going to do is to bootstrap, is to, with a sample with replacement from the original data set. Okay. And of course, we obtain the what is it called? The first booster sample. We compute, we have the estimate, we do that, we can find the average, we can construct or find whatever metrical measure. But what if in a situation whereby the distribution exists? Okay, so if the distribution exists, what we can do is, do they give us the maximum likelihood expression for the distribution? Because the maximum likelihood expression for the distribution will act as an estimator for that. Or whatever estimator given, it is that very estimator that you're going to plug in into as a parameter to simulate data set from that distribution. Then you do the same approach. Is there any question for me before I go today? Any question for me? Now you know how to assess the performance of your model, okay? Or depending on the nature of your data set, you know how to do that. Depending on whether the functional form exists or not, you know how to do that. We consider non-parametric or bootstrap in a situation or in a assumption-free inference where you don't know, we don't make a stringent assumption about the functional form of your model. But the parametric, on the other hand, you know the functional form. There are some functional forms that are complicated in a way you may not be able to figure out the variance of the estimator. If I cannot figure out the variance of an estimator, then I cannot measure uncertainty. Does that make sense? So a measure of uncertainty is the variance. So if the variance formula is complicated, then the bootstrap can help in assessing model performance. We're starting a new topic on Monday, a new chapter, okay? And that is actually going to focus on, I think, regression. You can check. I don't know. You can check the syllabus. You're actually going to. And I've also updated the date of exam, midterm one and midterm two. Initially I just gave the week, but it's going to be a Friday of those week. Does that make sense? Because I want that same week I want a situation whereby we're actually going to do revision, then before you have exam. Okay, so this is the end of the third week. Okay, we've done how many chapter now? Now, what I need from you, assess what you've done so far. Send me a message, rate your understanding, and you send me a message. You can also have it in this class. When I want a situation, my resolution in 2025 is whatever course I teach, all students they should have A. But you are going to be the one that will make it happen. Okay, when you get stuck, you let me know. Okay, I've shared the venue of my talk. Check the announcement. I'm having a talk on Wednesday at 150. I think I put, yeah, I think you're going to benefit a lot when you come for the talk. Okay, make sure you all stay safe. Have a lovely weekend. Bye for now, everyone.